or where science fiction falls apart because of all the things, if you take Star Trek, and I don't know how much experience you've had with Star Trek, but or Star Wars or any of them, of all the things, the most unrealistic of them all is the fact that they walk around those spaceships, right? That they're not floating around. There's no way you can make that happen. It doesn't, I think they at some point, I know in one Star Trek, they have a thing where the artificial gravity is turned off or something, but there's no scientific explanation for a gravity system like that. The only good one is something like this, a spaceship design like this, where actually, you would live in this portion here that's rotating. And I have a little video to show you what I mean. The idea being that it'd be centrifugal force, so to speak, that would keep you on the outside, that keep your feet grounded. Let's just watch this little video I have. This just shows sort of one that they've actually tested. This is actually like a NASA video of an artificial gravity situation, right? And this is a setup they've actually tested before. So by having this circular motion, so that's 10 times, that's only like point, like FG, it, so to speak, would be 0.98, right? It's pretty cool. So for them to be really sucked into the floor, so to speak, they would have to rotate faster. And there have been designs of spaceships for long-term space travel with this, but nothing's ever been built before, which is kind of too bad. But it does make me upset about the Star Trek and everything. I think they do speed it up a little bit. It's just, so you can see he's a bit more firmly grounded here. The thing is rotating faster. So that's just a model for artificial gravity, and with that model, we're going to try, let's see what this is. Oopsie, stop. Subject was pushed to accelerate. Right. So you can see that's like zero gravity, right? You can see he's barely connected. Okay. Anyway, so the circular spaceship is a design for to simulate artificial gravity. It's the closest you could do, something rotating to pull you to the outside, make you feel sucked to something, right? So the example I have relative to that is just a little example. Imagine you've got a rotating space station like this, and we know the radius, and then how many times per minute, the RPM, so to speak, would it have to rotate to produce a force equal to about 30% of Earth's gravity. So before you get into writing too much, just look over at the givens. We have R is 40, that's given. And we know that the AC, right, the centrifugal acceleration has got to be 30% of 9.8. Okay? And we need to know how fast. We're looking for RPM. RPMs are frequency. So when you solve for RPM normally, you're solving for rotations per second. That would be hertz, right? So if you can just see, I go through the calculation here, so trying to solve for F. And to go from rotations per second to RPM, just take your answer and multiply it by 60. If you do 0.043 in a second, you do that times 60 in a minute, right? And that's how you come up with the answer. And I think that's a reasonable number. I don't know too much about space travel, but 3 rotations or 2.5 rotations in a minute seems like a reasonable number. Okay, so that's just an example you could see on an assignment, or to be honest, probably not on a test. It's not a sort of important enough example, but you might see it on your assignment, something to do with artificial gravity. Okay, now here we're moving on to gravitation. Now we've talked about gravitation before many times. I know you know the formula. I know you know how to apply it. The thing, I have a great example of a harder problem related to gravitation that I want you to think about and be able to solve. And the problem is simply that there's a spot between us and the moon in which the force of gravity between whatever object is located at that position and the moon is exactly equal and opposite to the force of gravity to the Earth. Therefore, they cancel each other out. So at that point, there would be absolutely no force of gravity. So if any closer to the moon, oopsie, didn't mean to do that. Any closer to the moon, and you'd feel a stronger force of gravity between you and the moon. Any closer to the Earth, there'd be a stronger force between you and the Earth. So yeah, if this object was located in that location, yeah, I said this already, yep, the gravity would be exactly net gravitational force of 0. So the question is, where is that spot and how do you figure it out? Okay? And you know, the data that I'm giving you, and obviously if it was on an assignment, you might have to look that up yourself, but on a test I would give you this stuff, of course, that the mass of the moon and the mass of the sun, or sorry, the Earth, and then the center to center distance, like from here to here, is, well, that number, 3.84 times 10 to the 8 meters. So we're looking to find, you know, where's P, because at point P, there's no gravitational force. And you'll notice I don't know for sure, but I can be fairly certain. Well, I do know for sure. We know that it's going to be closer to the moon because the Earth is so much more massive, right, that if it was right in the middle, for example, you would have a net force towards the Earth because the gravity force to the Earth is going to be bigger. So the information that I've written down here, I'm just going to spread this out a bit more, is that if this is the total center to center distance, and say what I'm going to try to solve for is this P, the distance from point P to the center of the moon. Well, if that's what P is by definition, then the distance from point P and the center of the Earth would be the total center to center difference, take away P, right? And if that doesn't immediately make sense to you, just take a second and think about it just to make sure you're clear. Okay, so again, we're looking for this location such that the gravity force between any object and the moon and any object in the Earth are equal and opposite. You cancel each other out. So the way that you look at the solution then, I say at point P, any mass would experience the same force of gravity towards the Earth and the moon. So what I'm writing here is the force of gravity from point P to the Earth equals the force of gravity between point P and the moon. So let's go through the solution. It is algebraically a bit of a disaster, bit of a nightmare. But this looks awful, but just take a second with it. This is me just writing out the gravity formula. So mass of the Earth, and the distance is, of course, the center to center minus P, where P is really what we're solving for. Over here, that mass M and the mass of the moon, and there the distance is only P squared. So right off the top, I can calculate, cancel the G's, they cancel, and the small m's cancel. So here's my equation now. As I have written over here, we'll cross multiply. So ME times P squared equals MM times this mess. Are you terrified yet? I wouldn't put this on a test. It's a good question though, and this type of question could come up at another time. So looking through the solution or the analysis then, so I've got this equals this. I do want to substitute in the actual masses of the moon and the Earth, and I want to solve for P. The first thing I did, well, if you just look at it, there's the mass of the Earth times P squared equals the mass of the moon. Now what I've done here is I've expanded this, right? And to expand that, you know, this number would be this squared. This number would be 2 times this times P, and then obviously plus P squared. It looks awful, I recognize that, but you go through, this hasn't changed. This is me distributing the mass of the moon through. So this number, this times 10 to the 40 here, is the mass of the moon times this number. This number is the mass of the moon times this number. And then now you've got the mass of the moon 10p squared. And it's a quadratic. And just a quick thing on using the quadratic formula. So here's my awful numbers. You should be able to plug them into, if you have a quad solver, or if I haven't shown you this before, you can go online, quadratic solver. Let's see if this one's any good. Yeah, and you can put the numbers in. Now, I think sometimes, I think sometimes it gives you a hard time with the scientific notation, so you have to find the right app. What's the first? The first, my A, 5.9 times 10 to the 24. Let's see if it takes the 5.9. I'm going to say E24. You've seen me use that before. B is 5.6 E31. I don't know if it's going to take my E there. And last but not least, minus 1.08 times 10 to the 40. Those are some big numbers. Yeah, it did. Okay, so it liked the E. So that's something you can do, by the way, if you want to avoid using the quadratic formula. Or you could suffer, put yourself through the agony, and work that one out using quadratic formula. Anyway, so here's my solution. P is 3.84 times 10 to the 7. Funny, it's so close to, in digits anyway, to the total distance, right? So if we think about does the number make sense? Now you might say to yourself, well, it's awfully close to the whole thing. This is a great example where orders of magnitude, understanding them makes a huge difference. This is actually, well, if we take a calculator, this is actually 10 times closer to the moon than it is the Earth, right? It's exactly 3.84 and 3.84. Yeah. If you divided this by this, you'd get 10. So that means that it's 10 times closer, which I think makes sense based on their masses, right? So that's a great example with universal gravitation. And so I like my answer, by the way, because I expected it to be closer to the moon than to the sun, to the Earth, sorry. And that's exactly what happened. I have one more example. This one we've seen similar types before. This one's just saying, okay, we've got the Hubble, which is a space telescope that orbits the Earth, and it has an average height of 598 kilometers above the surface. We need to know, what we're looking for then is, what is the speed of this thing in order to keep it in orbit, and what's the orbital period, meaning how long does it take to circle the Earth? So the information I have, putting it in terms of r, because this is gravitation, is there's the 598 kilometers, but then I have to add the center of the Earth, or the radius of the Earth, to get the total r, the radius of the Hubble's orbit. I know the mass of the Earth. I don't know the mass of the Hubble, but that's okay. That probably tells us it'll cancel out. And the things we're looking for then is its orbital speed to keep it moving, and its orbital period, capital T. So all you do then is you set Fg equal to Fc. And you can see that I've started that down here. M's cancel, as they do. M's gone, M's gone. So it doesn't matter. Any satellite would be at that point. Rearrange for V. Let's just take the square root of this. So it's going 7,516 meters per second, which is fast, but you know what? It should be fast. It's traveling above the surface of the Earth. Okay, so to find orbital period then, you just use the fact that speed is the distance over time, right? And the distance this thing travels in one period is one full revolution, which is 2 pi r. So solving for period then, you just sub in the numbers that you know, and you get 5,800 seconds, or 1.6 hours. That does seem unbelievable, right? That means it circles the Earth in 1.6 hours. That seems unbelievable, but it's not. I know, for example, almost certain, let's just check. the orbital period of the International Space Station. I think it's 90 minutes. Should just come up with it. Yeah, orbits the Earth about every 90 minutes. So even though it seems like it's really fast, it's actually, it does make sense. Okay? All right, so that's it for gravitation mixed in with a little bit of centripetal force and just sort of that hard question like the moon question there.